My name's David Richardson. I'm the Vice-Chancellor here at UEA, and it's my great pleasure this evening to be introducing Professor Laura Bowater to you all, of course, to deliver her inaugural lecture. And of course, we're very proud of our UEA professors, and it's a wonderful moment when we have the opportunity to enjoy their inaugural lectures together and learn more about their research. Laura actually began her academic career a few years ago in the University of St Andrews, where she studied for a BSc in microbiology and biochemistry. And I should say, I'm a microbial biochemist as well, so these are disciplines that are very close to my heart. And in fact, Laura studied for her PhD in the University of Dundee, and that was from 1998, and she was working in the laboratory of David Boxer, who actually later went on to be the director of the Institute of Food Research here in Norwich, and she was studying how E. coli could grow using hydrogen as an energy source. Now, I don't want to reveal our ages, but I've actually known Laura for 25 years because we first met, because we were both bacterial biochemists, actually at a conference in Scotland, in the Scottish Highlands, way back in 1992, Kinloch Rannoch, and we might have done a little bit of whiskey tasting together. And what we did do was stay up all night, don't worry, we stayed up all night to watch the general election of 1992, when Neil Kinnock was supposed to get elected. Instead, John Major shocked everybody by being elected instead, and we watched each result come in, along with many, many other people, one by one that evening. But it was really a memorable conference, and as so often happens in life, and I was then working at UEA, Laura then at Dundee, things come round, and later on in 1998, Laura arrived with Richard, her husband, in UEA, and then in 1999 actually took on what was then a 6-month part-time position as a research assistant with Stefan Bornman in biological chemistry in the department of John Innes Centre, and as also so often happens, a 6-month position becomes an 8-year position, and so she was staying at the JIC for 8 years, studying bacterial enzymes and developing and extending her laboratory skills. She also learned to multitask a little bit. Well, more than a little bit, because she actually became an associate tutor with Open University and took on an honorary lectureship in the School of Biological Sciences at UEA, in addition to the JIC position. And she began to develop her passion for science communication and her interests and concern about the growing problem of antimicrobial resistance. She moved to Med as a teaching fellow in 2007. That's the School of Medicine here at UEA. And that was a significant career change, but also an opportunity to develop her passion for teaching and to communicating science. And also, she was and still is a staunch supporter of equal opportunities for everyone in both in higher education and the workplace. And she's done a great deal of work on that front as well. Laura's been chief editor or editor-in-chief for Microbiology, the Microbiology Society's magazine, Microbiology Today, and has made several media appearances in various capacities talking about infection prevention and control. She's also the author of 2 books, The Microbes Fight Back, Antibiotic Resistance, and Science Communication, a Practical Guide for Scientists, and that second book authored in collaboration with Professor Kay Yeoman, also from UEA's School of Biological Sciences. Both books, by the way, are outside and on sale, and Laura is very willing to sign them, so you walk away with a signed copy. As if all that isn't enough, Laura's currently Associate Dean for Innovation and Engagement at the Faculty of Medicine and Health at UEA, and so really, she's really very, very active on many, many fronts. It's wonderful that she's become a professor at UEA and that she's here today to share her work with us and her thoughts with us in this inaugural lecture. We're going to hear about antimicrobial resistance and the increasing problem that is, but I'm not going to steal any of Laura's thunder on that subject. I just want to now ask you to join me in welcoming Laura to deliver her inaugural lecture.
Thank you very much for that introduction, and thank you very much for the opportunity to come here today to tell you a little bit about something that I feel very passionate about, which is antibiotic resistance and how the microbes are fighting back. And if you've come here hoping to hear this talk, I promise it will start in about 10 minutes' time, But I had to take this opportunity to tell you about something else that I'm really passionate about, and that's myself and my story about how I got here. And it's not often you get to do that, so here we go. So my interest, I think, in science stemmed back from when I was a wee girl living in Scotland, and my father got a position working as a soil chemist in Uganda. And Uganda is an East African country which is on the equator. It's quite a poor country, it's a third world country, and he had been hired by the Overseas Development Agency to go out there and to help the Ugandans to begin to better utilise their soil in order that they could feed themselves well, but also to start exporting. And we worked on a research institute, which was in the middle of Uganda, and we were the British there, but there were Americans, Canadians, Danish, Dutch, a whole variety of different scientists had come together. And from the very get-go, from about the age of 2 or 3, although that's giving my age away, and I always lie about my age, except when my daughters are in the audience, because they always tell the truth, I always recognised that science was something that was multinational and people came together based on their disciplines and not from where they were from. But anyway, so when you arrived in Uganda, you touched down in Entebbe, and then it was a car journey through Zika forest, and eventually we ended up in somewhere called Serari, which was really literally the back of beyond, and it was a dirt road to get there. And there was lots of really interesting rules about living in Uganda when you were young. And these rules went something like this. Don't step on snakes, avoid spiders and scorpions, always keep something on your feet because something can crawl through your soles and get into your veins and end up in your heart. Never go swimming near the lakes, even though they look beautiful, because you'll get something called bilharzia, which was a really strange thing at the time. Never drink water unless it comes out of the silver canisters that we had in our kitchen, which was all boiled. And have to take your medicine regularly every day. And there were all kinds of things like this. And I could never really understand why that we had to go to these sort of big efforts. But my mum and dad always used to say to him, you can't see it, but there's things out there that can really hurt you and make you sick. And that, I didn't realise at the time, but it really struck with me and stayed with me for a long time. So we were there for a few years until this chap arrived. And those of you who are young in the audience might not recognise him, but he's a dictator called Idi Amin, who arrived and slowly started to dismantle the infrastructure that we had in Uganda. And it came to the stage that it was quite frightening to live there, and we were forced to flee across the border to Kenya, my family and I. And my dad was left behind to finish his contract if he wanted to get paid. So we left Uganda, moved back to the UK, and then sort of 6 or so schools later, we eventually ended back up in Scotland, where I had to think about going to university. And being in the family that I was in, my mum was a teacher, my dad was a scientist, and it was always assumed that I would go to university. And like David Richardson said, my first university was St Andrews, and you always have to have the curly 80s perm, so that's that one there. And then I moved to the University of Dundee to Professor David Boxer, who followed me to Norwich. I had to put this picture up because it's a really good friend, Tracy Palmer, who went to Norwich first, and I followed her to Norwich. This chap here you might recognise, because strangely we were in Dundee at the same time but didn't really know each other, and then ended up working together here at the University of East Anglia. That's John Winpenny. And then I met this chap here, who is Richard Bowater, and I followed him to Houston in Texas, where he had got posted to do a postdoc working in the laboratory of Robert Wells. And we moved there and got married, and significantly less than 9 months later, the reason why we moved was here, which is my first daughter, my first baby, Charlotte Bowater. After that, having spent 2 years there and avoiding significant tax, we moved back to the UK, and I had my second baby, and that meant that I'd been out of work for about 4 years. And during that time, I was sort of thinking, I'm never, ever going to get back into employment. Who wants to buy or hire someone who's been out of work for 4 years with 2 young children? It wouldn't be a risk that lots of people were prepared to take, but someone did take the risk. And that was Stefan Bornemann over in the John Innes Centre, who'd heard that someone was looking for a wee part-time job, and he was kind enough to take a gamble, took me on, and I worked there for quite a long time, and I learned a lot in Stefan's lab, and I really have to thank him for that. And he also gave me the opportunity to try lots of different things as well, to learn how to do some science communication. And the picture that I have in the middle here is when I started getting interested in doing science communication, but I had no confidence to stand up in front of people and do it myself. So I used to try and get other people to do it instead. And you can see here that I managed to persuade my husband to do it, and Tony Maxwell as well, and Mark Butner, who were also scientists in the John Innes at the time. And this was during the BA Festival of Science. And at that time, we also used to have a family affair, so my little daughter there was there helping to keep these things running well. And during my time at the John Innes, I did a joint project with Stefan and Mervyn Bibb, and it was something working on cinnamycin, which was a new novel antibiotic. And that's where I really started to get interested in the topic. But not interested enough to stay, because I moved over to the University of East Anglia and the Norwich Medical School. And again, it was someone taking a chance on me, I felt, which was Sam Leinster, who took me on as a teaching fellow, even though I was working in a plant research institute, and there's not a lot between plants and medical schools, but he saw potential still. And it was at that time that one of my colleagues, Kay Yeoman, absolutely worked with me and really made me develop a long way down the path of becoming someone who's really interested in doing science communication. And like David Richardson said, there's a book there that will tell you a little bit about myself and the work that we did together on that point. And then also, what I have here is that when I came to university, I had absolutely no skills really as a teacher. I had a passion for it, but I didn't know how to do it. But being at the University of East Anglia, we were encouraged to go and do courses, and I managed to graduate with an MA HEP, which is a Master's in Higher Educational Practice. And all these things led to me standing here in front of you today, giving my inaugural lecture called The Microbes Fight Back, the Growing Problem of Antimicrobial Resistance. So what I am going to tell you is that we are genuinely facing a global threat when it comes to this. And I hope by the end of this session that you will recognise how important antibiotics are, know what antibiotic resistance is and why it happens, why this is going to be a problem and is a problem, and also the steps that we can do to slow down the inevitable. But I'm going to start this sort of tale way back, going to take you back to France, and this is 17th century France, and we have a fairy tale here. And this fairy tale has a bit of a strange premise, if you think about it, like all fairy tales, but it goes something like this, that a much beloved princess had gone to a party, and at that party, her christening, she had been put under a curse or a spell by an evil witch who'd said that when she reached her 18th birthday, she was going to prick her finger on a spinning wheel and die. Now, luckily, there was a good witch on standby, and that spell was ameliorated somewhat. And in fact, all that happened is she fell to sleep for 100 years. She had thorns that grew up around her, but a kiss from a handsome prince and everything was hunky-dory. Now, a bit far-fetched, that fairy tale, except for the part that probably in 17th century France, if you did get a cut to your finger or a break in the skin, there was a really good chance that that could turn into something that was really quite serious. And in fact, it could even kill you. And I know this because if you look at statistics that had been gathered from the National Office of Vital Statistics in America, I found out, love gathering statistics, especially statistics about causes of death. And I'm not expecting you to read this, but just to understand that at the turn of the 20th century, 4 out of the 10 top causes of death were caused by infectious agents like viruses and bacteria and fungal infections. And infection stalked the world at that time, and everybody was really scared of infection. And as a community, I think we've sort of lost that fear. But luckily, the 1900s were about the time when there's a huge renaissance in microbiology and microbiologists. And a lot of work had been done to understand how these tiny creatures that you couldn't really see by the naked eye, you could only see them under microscopes, what they looked like, how they behaved, what they had in them, and vitally, how they are different from the cells that we have in our body. And they were also beginning to understand how something so small and so tiny could cause your food to go bad, but also could cause us to get so seriously sick that, in fact, it could lead to death. And this was a turning point, if you like, because there was somewhere who just had this sort of seminal moment, this seminal thought, when it kind of dawned on people that, in fact, if we could find a magic bullet, a chemical or some kind of compound that we could use to target a bacterial cell and not affect our human cells, then maybe, just maybe, we had a potential for a medicine that could destroy those bacteria but leave us unharmed. And perhaps the most famous of these magical bullets is one that you will have heard of, which is penicillin. Penicillin, it's rumoured, and I think it's quite a good rumour, was discovered in 1928 by one of my favourite scientist, Alexander Fleming. And I love Alexander Fleming because he is a Scottish scientist who'd moved down to England to do all his work and his research. He was a great microbiologist, and actually his lab husbandry wasn't the best, and I feel that I have lots in common with him. Now, what was also interesting about this chap is that he was a physician, a doctor, who'd spent a lot of time working in France in the trenches during the First World War. And he became profoundly affected by the fact that soldiers were getting injuries that they should have been able to recover from. But these injuries became infected, and it meant that there was amputations, or in fact, these soldiers lost their lives. And he returned to Britain, to his work, with a passion that he wanted to find something, this magical bullet that meant injuries like this in the future weren't going to be such a problem. And he did a lot of work, but unfortunately, even though he published it, he wasn't a great science communicator, and he actually wasn't a particularly good biochemist. But what he did find was when he returned from a holiday, and in those days, scientists went on huge holidays, so they went on holidays for about 6 or 8 weeks during the summer, and Fleming had a summer home in our region, just on the border between Norfolk and Suffolk, somewhere called Tuddenham, that you probably see on the A11. He has a house there. So in the summer of 1928, he went to his house, and on his return, he found this plate on his bench. Now, if that was me in Stefan's lab, what I'd have done is pick that plate up and discreetly put it in the bin so he didn't even know that I'd left it lying around. But not Fleming. He looked at this plate and he saw something very, very interesting. He saw that the bacteria he was studying, Staphylococcus, the ones at the top of the plate, were incredibly juicy and creamy and plump, and they were quite well and healthy. But the plate had become contaminated with something called Penicillium notatum, a fungus, and the bacteria around it were sick. They were poorly. And he put 2 and 2 together and reckoned that it meant that there was something that was being secreted by that fungus that was starting to destroy the bacteria around it. And he got really excited at this point, but he couldn't do anything with it because he wasn't the best biochemist in the world. And it languished on the shelf, that work, for about 8 years until this group of scientists working in Oxford University picked up his work, and they decided to proceed with it and to see if they could do that next step, if they could purify that substance that they found. So Florey, Heatley and Chain did fantastic work. They got his fungus, they began to grow it in vats in the laboratory until eventually they got a small vial of unpure penicillin, but it was enough that they felt they could start to do some really interesting experiments. And the first experiment they used was animals. So they had some mice that they infected with some known pathogens that they knew were going to cause disease. And when they gave it, the mice got really sick. But when they gave some of the mice the penicillin, these mice recovered. And immediately, these scientists could see that they were onto something really special, something that could actually change modern medicine. And they went to the British government and asked for funding, but their timing was terrible because this was 1940s, it was the start of during the Second World War. The British government had no money to devote to this sort of pharmaceutical research, and also there was a bit of disagreement about how it should be funded, because at that time the British government could see the potential and they were determined that no one would be able to patent that drug. So these scientists were forced to move to America, where the Americans embraced it hugely, started to produce loads of it under factory conditions, and it changed the outcome of the war for them. And they also had no scruples, and they patented it. And so when we wanted it back after the war in the UK, we had to pay the Americans shed loads of money to get that drug back with us. So there's a lesson there to be learned somewhere. Anyway, the first person to get this drug was somebody called Albert Alexander. And they'd been looking for a person to try the drug on for a wee while, and this person fitted the bill. He was a policeman working in Oxford at the time, and there are two stories about how he got his infection. And the first was that he'd scratched his face while in the garden, and his face had got infected that way. But probably the most likely one is that actually in his off-duty, he was an air raid warden. And at one point, some rubble had fallen and it had grazed his skin, but nevertheless, he got a bad infection in his head. So significant that by the time he went to the doctors, the GPs, they knew straight away that he wasn't going to recover from this, and he would become the perfect candidate to try this new drug on. So he took the drug, and within 2 or 3 days, the transformation was amazing. His temperature dropped, he started to eat again, he started to perk up, and it looked very, very hopeful. But they ran out of the penicillin, and even though they tried to purify it from his urine, there just wasn't enough, and eventually, sadly, Albert Alexander died. But it was a death, I think, that led to some really, really positive things along the way, because it led to the golden era of antibiotic discovery. So this whole story inspired other microbiologists to go out, search the world for new soil compounds or to find bacteria in interesting new places and to see if they were producing interesting drugs. And they found lots, and they started to fill up the pharmaceutical shelf with antibiotics. And you had the fantastic biochemists who started to understand what these drugs were and to see what they could do to produce more of the drugs and to tweak these drugs so that they were making even more semi-natural compounds. And again, the shelf started to get really full. But we also had the chemists who took things one step further and they think, well, let's avoid the bacteria altogether and let's start making these drugs in the lab using man-made means. And we eventually, by the late 1960s, had a huge shelf of really good drugs that were effective, life-changing drugs that we thought were going to last forever. In fact, everything was so positive that the US Surgeon General, William Stewart, told Congress that we should close the book on infectious diseases. We needn't be worried about them anymore. Now, as with all things American, it was quite an American-centric vision of the world because actually, if you look at these statistics from the top 10 causes of death, and I know it's a pretty rubbish graph here, but what I just want you to see is that this is high-income countries on the left. And the arrow you can see is one of the causes of death that's probably caused by infectious agents. But this one here on the right, which has 7 or so arrows on it, is from low-income countries such as Uganda, where infectious diseases are still the biggest killers. And there are lots of countries that are in that pile today, really. But being a good microbiologist who studied microbiology for a long time, and my university education told me that luckily pathogens, the bacteria that cause these horrible diseases, they're quite interesting and unique creatures, and there's not a lot of them. And most of the bacteria that we come across in our everyday lives are not harmful for us at all. In fact, some of them are positively good for us. And you're sat here in front of me today as an audience, and there's lots of humans, but actually half of you is bacterial cells as well. And I think that's something that is important to tell you, that you have this whole wealth of old friend bacteria that you have been born with, and it's changed slightly. They're a bit like fingerprints. So your sort of microbiome of bacteria that are healthy bacteria that help you to extract the energy from your food, and they prevent other pathogens getting in by almost coating your skin. But these microbes are part of something that we call the human microbiome. And it changes as we go through life, and it changes according to whether we've got pets, who we hang out with, where we live. And you're breathing in bacteria now as you're sitting here, and as you're sitting here, you're shedding bacteria from your skin cells as well. And most of the time, they do absolutely no harm whatsoever. And this here, you can see, is one of the bacteria, and it happened to be the one that Fleming was studying when he first came across his interesting fungus, penicillin, and it's called Staphylococcus. And this is a petri dish of someone who's just stamped their hand on it. So you can see that most of the time, these lovely, plump, creamy bacteria are the ones that are on your skin. And they're commensal, they don't do any harm, they're on your skin, they're up your nasal passages, they love mucous membranes and in your groin region as well. And if they stay there, that's cool. But this is a picture of a wee girl who's suffering from a skin condition called impetigo. And impetigo is a pretty nasty thing. It's sort of itchy, it can be a bit sore, and it's also incredibly contagious as well. And this little girl had had a cold, which had lowered her immune system. Toddlers, they've always got colds, they have about 6 a year. It had meant her eczema flared up, so she had bits of broken skin. And because her personal hygiene was pretty rubbish, her nose was dripping and she was just rubbing it into her broken skin, and this was the result. Now, I could have left it 6 to 8 weeks, it would have cleared up, but I didn't want to do that because I had to go back to work, and the nursery wouldn't take her when she had skin like this, which I don't understand. But I wanted to get rid of this infection really quickly. So she got treated with something called amoxicillin, which was a fantastic drug, and I'll explain why. So this is a lawn, this Petri dish has a lawn of the Staphylococcus epidermis, which was on Ellie's skin, and she was given amoxicillin, which has, that little paper has been dipped in it, and you can see that bacteria don't want to come near it. And that's because that this particular bacteria, it's really sensitive to that antibiotic, so it's a really good antibiotic to use. And 60% or so of the audience, this is the Staphylococcus that you have. It's this lovely white one. But not all of us have that. And there's about 40% of us or so who've got a different one that's called Staphylococcus aureus. And I know that I have Staphylococcus aureus. And aureus because it's golden. And again, when it's just on your skin and you're well and you're healthy, it's a commensal bacteria. It doesn't do you any harm at all. But you can see here, this is Ellie, who's got her skin cleared up. I forgot to say this, but if you want to see, in fact, that it leaves no scars, I give you full permission to check Ellie's chin after this talk. She's down at the front here, and you can see that actually the antibiotics work to treat. But they don't always work. And sadly, this is a histological slide taken from some toddlers who had got a Staph aureus infection that had got into their bloodstream and caused these little children to have sepsis and septicemia, and sadly they died. And unfortunately for us, Staphylococcus aureus is probably one of the most famous superbugs that that you might have heard about. And in the past, up until the early 1970s, penicillin was a great drug for treating any infections caused by this particular guy. And then it stopped working. But we weren't worried about that because we had our shelf, chock-a-block, full of other antibiotics that we could use. And the next one we went for was methicillin. Methicillin worked fantastically well, probably till the late 1980s, early 1990s. And then there used to be cases of Staphylococcus aureus that just weren't responding to this drug. So they were methicillin-resistant Staphylococcus aureus, or MRSA, one of the superbugs, the first one that really began to hit the headlines and started to scare people. And this is a graph that tells you the incidences of methicillin-resistant Staphylococcus aureus, or MRSA. And you can see here that in the Scandinavian countries, they don't have a big problem with it. Around the Mediterranean, about 50% of isolates are resistant to methicillin. In Britain, we're somewhere in between, so that's about 10 to 25%. And in the audience here, probably there's about 2 to 5% of us actually have methicillin-resistant Staph aureus on our skin. And it isn't a problem if we're well and healthy, but if you need to have an operation or something like that and your immune system is repressed, then it's something that the doctors really get worried about. And it's not the only superbug that we have out there. This is a list of something called the escape superbugs, which are new and emerging bacteria that are known to cause quite significant clinical infections. And clinicians around the globe are exceptionally worried about this list of bacteria because they're becoming more and more resistant to the antibiotics that we have. And it's not a finite list either. So what we also have are, in our country, we have gonorrhea that is becoming increasingly hard to treat with the antibiotics that we have. Around the globe, we have tuberculosis, which there are some strains of that now that are resistant to everything that we have. Anything we throw at it, and those bugs, they come back fighting. So they've always been magic bullets for treating infection, and we still rely on them for that. But what you might not have realized is that not only that, they have changed modern medicine. Most of us sitting here at some time or other have had antibiotics for infection, but what you might also have had antibiotics for is if you've ever had to go to get an operation in a hospital. In the old days, operations were something that was a last resort. You only did it if there was no other options, because the chances are you die from an infection. These days, we don't have that problem. We can take antibiotics prophylactically, and it protects us from that sort of invasive technique of getting those bacteria that are out there into our bodies. And even if we do, the antibiotics really help us. And those of us who've got new hips or new knees, who've had heart valve operations, anything like that, we'll have benefited from this. It was also good for childbirth. It used to be a huge killer for women who got infection that way, but it's really, really changed modern medicine. And even things like cancer therapy, if you're having cancer therapy, it knocks out your immune system and makes you really prone to infections, but it's because of antibiotics that our recovery rate for cancer has slowly begun to creep up and is still creeping up. But every time we take a dose of antibiotics, we pee it out into the environment. And our environment is becoming polluted with low levels of antibiotics that didn't used to be there before them. As well as that, we're putting antibiotics into the environment, but also agriculture, the agriculture that we're using, which is relying on antibiotics to keep herds safe because they have husbandry now. That means that you have animals in close quarters, means that they're relying on antibiotics, and animals pee out antibiotics too. So it means that we're getting antibiotics into the environment from all kinds of sources. It's in water when we're farming fish, we use it in apiculture for bees, and also the whole process of factories making antibiotics mean that antibiotics leach into the water system, and we have water systems that are highly contaminated with antibiotics. And this is a problem, and it's a problem that Fleming spotted way back in 1945, and he told us about it in his Nobel Prize acceptance speech, when he said, look, guys, if you're going to use antibiotics, use them well, use them at high doses so that you kill off everything, because if you don't, and they're left in the environment at low levels, you're going to get antibiotic-resistant bacteria developing. And he was right. And this has become a problem. Now, this infographic is taken from a review on antimicrobial resistance. And this review was commissioned by David Cameron. And unfortunately, it's something I have to thank David Cameron for. It's a really good thing that he did. And I just want to point you out two petals here. So the first petal is the big blue one. So that's the present time, and it's the number of deaths globally. And you can see here that we have 8.2 million deaths a year caused by cancer. It's the biggest killer that we have at the moment. Move up to that purple petal, and you can see a wee strip at the bottom, a blue strip at the bottom. And that's the number of people at the moment, about 700,000 annually, so a year, who are dying of antimicrobial resistant infectious diseases. But the purple is the projection of how many people are going to die if we change nothing, if we just carry on as we are. And they reckon that by 2050, it's going to be the biggest killer that we have in the globe. So we're back to the old days, really. But the old days, but worse, because those bacteria were actually able to be destroyed with antibiotics, and these ones aren't. And let me just show you, this is a great video that just shows you how quickly this can happen.
So what we ended up building was basically a petri dish, except that it's 2 feet by 4 feet. And the way we set it up is that there are 9 bands, and at the base of each of these bands, we put a normal petri dish thick agar with different amounts of antibiotic. On the outside, there's no antibiotic. Just in from that, there's barely more than the E. coli can survive. Inside of that, there's 10 times as much, 100 times, and then finally the middle band has 1,000 times as much antibiotic. And then across the top of it, pour some thin agar that bacteria can move around in. The background is black because there's ink in it, and the bacteria appear as white. First, you see they spread in the area where there's no antibiotic, up until the point they can no longer survive. Then a mutant appears on the right. It's resistant to the antibiotic, it spreads, until it starts to compete with other mutants around it. When these mutants hit the next boundary, they too have to pause and develop new mutations to make it into 10 times as much antibiotic. And then you see the different mutants repeat this at 100. And after about 11 days, they finally make it into 1,000 times as much antibiotic as the wild type can survive. And so we can see by this process of accumulating successive mutations that bacteria, which are normally sensitive to an antibiotic, can evolve resistance to extremely high concentrations in a short period of time.
Thank you, Harvard Medical School. 11 days. So the bacteria, they take on these mutations, and you know what? If you are a bacteria and you're in an environment where there's no antibiotic, and even if you have a mutation that makes you resistant to an antibiotic, it's not a big deal because you don't need to use that. It's only when you have antibiotics in the environment that having a mutation or being resistant to an antibiotic becomes an advantage. And I just want to show that to you here. So the first guy, that fuzzy bacteria in the first one, he's an antimicrobial resistant bacterium. The other guys, they don't have any of those genes and they're just sensitive to antibiotics. But it's not a problem because there are none. Add antibiotics into the mix, and what you can see here is the sensitive bacteria, they die. The bacterium that has the resistance is left, and it divides and it multiplies, and over time it becomes the one that's there, the most popular one. And even when you take the antibiotic away, that's what you're left with. And every time we have an antibiotic and we use an antibiotic, that's actually what's happening to our good guy bacteria, our microbiome of bacteria that are in our gut. So that's something worth thinking about, really. And don't get me wrong, sometimes we really need antibiotics, so we have to take them. But it's just worth remembering what else is going on every time we do that. And how quickly does this happen in real life, and how has it affected us? Well, what you can see here is the lozenges down the side are antibiotics when they were discovered. The C is when they started to be used clinically. And maybe one of these antibiotics is one that you're familiar with, one that you might have had or used. But you can hopefully see that we had this golden age when lots of them were discovered and taken into the clinic. Recently, we've had a couple more that have come through that we've managed to find or create. But watch how quickly resistance came onto the scene. So those later antibiotics, the one we're very proud that we've made and we've got them coming through, there was resistance to these particular antibiotics before those drugs even hit the clinic to be used clinically. And this is a process that we're in at the moment. So it really is a concern. And since the 1980s, we had that golden period in the 60s, but we've only had 5 new classes of antibiotics come through. Well, what are we going to do? I guess increased antibiotic discovery has to be on there, and that's, so obvious, really. So we have to try and encourage pharmaceutical companies to become more involved in doing this. And I can say, hand on heart, that I feel quite hopeful because we've got small laboratories around the world who are actively researching, trying to find new antibiotics. And we're doing that here at the UEA as well. And as well as that, we've got labs out there who are starting to study how bacteria are getting the resistance to see if we can begin to tackle it that way. But we have to remember that even if we find a new antibiotic and we spend that 20 billion or so getting it from laboratory into clinic, it takes about 20 years. And that means that one that we find today is going to be 20 years' time before that one comes through. And I think that's about 2037, before we're going to have that at our use. And also, once we have it, what's going to happen is that we're going to say to the pharmaceutical companies who've invested that, we don't want to use this really. We want to keep that on our shelf as our standby, our last resort antibiotic, because we don't want to squander it. So of course, if you're a pharmaceutical company, it's not a great investment. And I think that's something that we need to remember. Plus the fact that it's really difficult finding new antibiotics. When we're finding something that has potential, what we see is that in actual fact, it's the same thing that we found those 50 or so years ago. The other thing is that we can stop using antibiotics like we're doing at the moment, and we can reduce our use of antibiotics. Back to the States, I told you the United States love gathering statistics, so lots of these infographics now are from America because they're they have a fascination with them. And it's worth pointing out that 30% of antibiotics are used by humans, 70% are used by animals in their agricultural business and their agricultural husbandry as well. Now, lots of us in the audience are probably thinking that's really terrible that they're doing this, but you have to remember that this is consumer driven, that we are very dependent these days on cheap, good quality meat, and the only way that we can get that to feed the population that we have is by growing animals in conditions where they rely on antibiotics. Now, I'm actually have a bit of tongue in cheek here, and I will go back and say that in Europe, we started to look at this, and we don't use antibiotics as readily as they do in America anymore. And we've made the decision that, in fact, the antibiotics that we feed our animals are completely different to the ones that we use in the clinic. And we are beginning to reduce the ones that we use in our livestock as well. So it can be done, and we're all sitting here today and none of us are starving. So I think that's something that we have to bear in mind going forward. The other thing is that there's probably, from America again, if you look at this, what it's saying is that this is a graph from people who've got an upper respiratory tract infection. So they've got that cough or that sore throat or, that horrible chesty cough that they can't get rid of. And they've gone to the doctors to get antibiotics for it. And in actual fact, probably 27 million prescriptions are for antibiotics that just aren't going to work, because that infection you have, it's not a bacterial infection, it's a viral infection. And you can give every single antibiotics that we have to a viral infection and it's not going to make any difference whatsoever. So again, we love our antibiotics, and when we go to the doctor, we want to feel better. And I completely accept that. I was the same when Ellie had her infection. I knew it would clear up, but I wanted her to get better quickly. So it's something that we have to get the balance right. But perhaps something that could make a difference is if we went to the doctor, they took a sample, they put it into a machine on their desk, and they got the result back quickly that said, yes, it's bacterial, or no, it's viral. And then that would give us more confidence when they turn us away and say, just go and get some bed rest. And that's something that we're absolutely trying to track as well. But the most important thing that everyone here can do is to stop getting, or reduce your chances of getting sick in the first place by washing your hands. As a society, in fact, globally, we're terrible at washing hands. We think we wash our hands well, but in fact, we don't. And if we just learn to wash our hands better, so every time that we use the bathroom, although that you shouldn't even have to say that, but I will, every time we prepare food, every time we come in from outside, it would be really helpful if you washed your hands. And I don't mean wash your hands as in you go into the bathroom and you put the tap on and you put your hands underneath and you pull them out and you dry them. I mean, go to the bathroom, use the soap, wash your hands for about 2 rounds of happy birthday and then dry them. And by that time, hopefully, you'll have got rid of that bacteria that's on your hands. And it really is one of the best ways that we can be doing now to reduce infection. And if you think about it globally, the reason that infectious diseases are so rampant in developing countries, low-income countries, is because their ability to get clean water just isn't, and soap is just not as good as that we have here. We have it, but we're not using it properly. So we've got a few long-term solutions. So we can make better drugs, we can have good diagnostics, we can really look at surveillance to make sure we can see what's coming. We've got new therapies that we can use instead of antibiotics, and also really good infection control. And one thing I would like to highlight here is that at the UEA, we have research that's working in all these areas, and I'm very, very proud of that. So we've got Matt Hutchings over in the School of Biological Sciences, who's looking at his drugs from ants. We've got diagnostics, Justin O'Grady, and in my school who's doing this, surveillance, which we have David Livermore who's working on that. New therapies, Michael MacArthur, who's also in med, who's working on that, and infection control. Everybody who's interested in this does a little bit of it, and it's something that I feel very passionate about too. And a project that I'm doing at the moment is this one, which is Antibiotics Unearthed, and I would just like to thank Gary, who was part of the PhD team and has absolutely supported me with this, and also Eleanor Nardi up at the back from EDU. So Gary's in bio and Eleanor Nardi's in EDU. And it's a fantastic PhD project. And this is my PhD student here as well, who's Ethan, who's the one in the t-shirt who says, ask me about antibiotics unearthed. And just a wee quick self-indulgent video, if you like. It just tells you a little bit about this project. Antibiotics on Earth is a project that we're running with the Microbiology Society. So it's a citizen science project where we're getting members of the public to go out and gather soil. And what we're doing is looking at that soil to see if we've got some bacteria in it that might be producing new antibiotics. So that's part of what we do. The other thing is I've given a few lectures on this subject now, so I'm starting to get the word out there. And again, it's something that I think is very important that we could all be doing once we leave here. It's going and telling our nearest and dearest that we need to have better infection control. My book, they asked me to make sure that I tell you about my book. So this is my book here, it's outside. I'm happy to talk to you about it. And I wanted to put this photograph up here because it was a family affair, as all my stuff tends to be. And my sister was so good at reading lots and lots of versions of the chapters that came through to her, and she's a really good editor. So I'm sure that if anybody needs anything edited, Claire's your girl for that. And my brother as well did some of the beautiful graphics that you see in it, including the front cover. And they just did that because they're just really lovely relatives to have. We did science cafes on this, and I just wanted to put that up here. So we have a science cafe that we run in the Cut in Halesworth. If you're ever out that way, please go. They're fantastic. And we've done a couple on science antibiotic resistance there. We have a MOOC on this at the moment that we've got through our faculty, which is using infection control to combat antimicrobial resistance. So if this has piqued your interest, I was going to say it's free, but actually it's not. Sorry about that. But you can go and you can buy yourself onto this MOOC, and it's excellent, I have to tell you that. And then what I almost want to finish my talk with is just highlighting the fact that we have this wonderful project that is just launching tomorrow with the Science Museum, who've got a new exhibition called Superbugs, The Fight for Our Lives. It has some of the science that we do here at UEA is being highlighted as part of this exhibition. UEA is sponsoring it, so you will see our name closely associated with it. It looks fantastic, it's free to go to. We're off on taxis back at beyond time tomorrow morning that I can't even think about to get down to there for the opening in time. But it looks amazing, and I'm incredibly proud that UEA is associated with this. And because it's my inaugural and I'm going to self-indulge myself a bit more, I wanted to finish just with, I felt, some of the top tips for life in academia. And these are some of the things that I've picked up, I think, and just wanted to share. And the first thing that I would say is how I got here today is that quite a few people in the audience actually seeded me with self-confidence. They just said something or made me feel a certain way that I've just thought, you know what, I might be nervous, but I can do this. And I try my best these days to do that to other people as well. Knockbacks, doesn't matter what stage you get to, there's always an opportunity for you to get knocked back. And it happens a lot. But rather than just thinking, oh, this is just terrible, actually use that to learn from it. And my eldest daughter is fantastic at doing this, and I've learned a lot from her about that. I 100% think collaborating and communicating is the way forward. The more that we can do that, the more that we can work together, have interdisciplinarity happening, that's how we can absolutely make a difference. Feedback, feed forward. Take feedback wherever you get it, even if it's negative feedback. Use it to your own advantage, and be generous enough to give it to other people as well. Keep learning and give learning. I cannot believe sometimes that when I wake up in the morning, I get to come into university to work with people who have this incredible knowledge and passion for learning that they want to share with other people. And I have learned such a lot from being in this kind of environment. But we all got here because someone gave us learning. So I just think, just take any opportunity you have to give it back. Privilege is a privilege, and this is something that I've been thinking about a long time, is that we shouldn't just assume that we are here because we've worked really hard and we deserve it. Sometimes it's because we happen to be born in the right place at the right time, and not everybody has that. And we should be working really hard to ensure that we give opportunities for other people who haven't had that privilege to get opportunities to come to university, to be here, to be part of what we do here. And I guess that kind of comes with celebrating diversity. And I genuinely think all my sort of scientific career, we had opportunities for meeting different people from all aspects of the globe to come together to really make things happen. And that's how progress happens if we just have diversity. And finally, to thine own self be true. Just stick to your own beliefs and your morals. Obviously, there are times when you have to change what you do because it doesn't naturally fit with you. But if you can just hold on to the core of who you really are, then I think that's how you can get to eventually stand up here today telling you about some of the things that I've been lucky enough to achieve in my life. And I'm not sure what the time is, but these are some of my make a difference people, the people who've made a difference to me, and I want to thank every single one of them. Also, I've got a list here of other people who have just made a huge difference to me. My friends here in my book group, you've just been brilliant girls. My family, we never get together these days because we're sort of a very international, diverse family, but this is quite a good sort of, well, we've got quite a few of us together at that time. My mum and my dad, my lovely daughters who came here today, and lastly, my husband, who I wouldn't be here if it wasn't for him, really. But thank you very much for listening.
So, well, thank you, Laura. My name's Dylan Edwards. I'm the Pro-Vice Chancellor for the Faculty of Medicine and Health Sciences. And it's my pleasure to give a vote of thanks to Laura for a wonderful talk today. I mean, as you've seen, Laura is a fantastic communicator and an inspirational teacher, and that comes through in everything that we've heard tonight. And I should say as well that she's a wonderful colleague as part of our Faculty of Medicine executive team. It's a person that you can trust to get things done, and that's again where you see tonight. That we are facing a major challenge here, and this is a real crisis that we have to contend with. The re-emergence of infectious diseases from to situations as we would have faced 100 years ago. Some of us won't be, most of us I think here will all have been born in the antibiotic era, but we'll have stories from our relatives from the before times of what it was like. I know I had an uncle who died of peritonitis from a ruptured appendix, and these things are going to be issues that we have to contend with again if we can't get things under control. So this is a wonderful, a fantastic story that you're telling us, but scary as well. But the good thing is, as Laura says, that there is a wonderful weight of research activity that's going on here in the Norwich Research Park. Most of you probably don't realise, but we have one of the, if not the biggest concentration of microbiologists in the whole of the UK. And as you see, the work that is going on here that Laura's highlighted is really directly relevant to these problems here. So, will you join me now in giving an official thank you to Laura, and then we'll ask her to open up and answer some of your questions. So thank you again, Laura, for a wonderful presentation.